Hey everybody, just putting together a little calculation video to help you guys with the post-lab questions. They can be kind of confusing and misleading to work on your own. For all these calculations, I'm using just kind of general values. They're not the actual values from the lab video, so don't just write my answers down. They're not correct. But we're going to start with the first question. Using the volume of the titrant at the equivalence point, calculate the molarity of the acetic acid. So basically what we need to do is take that volume of titrant that we used and its concentration, so its molarity, and since at the equivalence point we needed equal moles of NaOH to neutralize all the acetic acid, that the number of moles there is equal to the moles of acetic acid that we started with initially. So if we had 21 milliliters of NaOH and it was, and this isn't the correct concentration, but let's just pretend it was 0.1 molar, okay? How many moles is that equal to? Well, we can just rearrange our molarity equation, right? Molarity equals moles divided by liters. If we know our molarity and we know our liters, we can solve for just moles. Okay, rearranging our equation, molarity times liters equals moles. And that is equal to 0.01 molar times, and again, I just made up this volume of NaOH, 21 milliliters. That's not the actual thing. Check the lab. Check your lab video in your notes. But just using these fake values, okay, the moles, if I plug this into my calculator, is equal to 0.0021 moles of NaOH. So that's how many moles of NaOH, that titrant that came out of our burette, were needed to neutralize all the acetic acid. Okay, I'm just going to move this over to give us a little bit more space. Okay, so our volume of acetic acid, remember we took 5 milliliters of our vinegar. We don't know its concentration, but we do know how many moles we need, right? We said we needed equal moles of NaOH, equal moles of acetic acid. So if we know our moles, we know our liters, we can solve for the molarity, which is what this first question is asking us. All right, so let's plug in our values. All right, so same number of moles, right? 0.0021 moles divided by 0.005 liters. That's 5 milliliters. All right, and that gets us 0.42 molar concentration of acetic acid. This is not the correct answer, right? I just kind of made these values up. Use the actual data from your labs. But this is kind of how you'd set up that first question. Cool? All right, so let's move on to our second question. Determine the Ka value of the acetic acid from the initial pH value recorded in step 3. So this is kind of broken down into 4 different steps. Let's start with step A. The pH value gives you the equilibrium H3O. Okay, H3O, that's hydronium ion. Why does that happen? Well, if you kind of think about it the pH value is a way of expressing how many H pluses or protons are floating in solution. Okay, those are all going to react with water and form H3O plus. And so if we know the pH, right, how much H plus is floating around, we can also determine how much of the hydronium is going to be formed. Okay, at equilibrium. And we're just assuming all the H plus is being picked up by water and turning into H3O plus. All right, so we just have to use the definition of a negative log, right? P is a negative log. So if we rearrange this equation, all you have to do is take 10 and take it to the negative power of the pH. So your H3O plus concentration at equilibrium is 10 to the negative 2.52. Okay, this equals 0.00301995. All right, let's move on to step B. The molarity calculated in step 1 above gives you the initial concentration of HC2H3O2, or acetic acid. Okay, this is just our value that we got from question 1. Again, this isn't the exact value, I just made this number up, but let's just continue with these made up numbers I used. Okay, so that's B, pretty easy because we already did it. All right, nope, messed up my ice table. Step C, let's make an ice table. So we need an ice table to calculate the equilibrium concentrations of acetate ion, which is C2H3O2 minus, and the acetic acid concentration, which is the CH3CO2H. Okay, so this is my reaction that's happening, right? My acetic acid plus water, and my acetic acid loses that proton, becomes acetate ion, and water then becomes H0 plus or hydronium. All right, so make sure you get your states of matter here. All right, so my initial concentration of acetic acid, which we calculated in the first question, 0.42 molar, again, made up value. And our initial values of our products should be 0, right? I shouldn't have any products when I initially start. Okay, but if you do remember from step A, we calculated the equilibrium concentration, okay? 0.0030199 molar. And you can actually see, if you look at your ice table, you started with no H3O plus, no hydronium. There was some positive change, and then it turned into 0.0030199 molar. So obviously the change from 0 to 0.003 ... is that. X is equal to that, because it went from 0 to that. That's what X is. So now all you have to do is go back in and plug in your value of X, and you can get all your equilibrium numbers, or concentrations, excuse me. Take those values, plug them into step D, which is calculate the Ka. All right, so after I finish putting all of these down, yeah, and then all I have to do is just plug these values into my Ka, right? Ka is equal to my concentrations of my products over my reactants. Plug those in, solve for it, and that's your answer for that. Okay, now we're going to move on to question number 3. This one's actually a lot easier than the previous one. Determine the Ka value of the acid from the graphical determination of the pKa value using the Henderson-Hasselbalch equation. Okay, it's a mouthful, the question, but if you kind of break it down, let's actually think about what we're doing. So the first step tells us, and I'm just going to write down the Henderson-Hasselbalch equation, right? The pH is equal to the pKa plus the log of my products, which is the acetate ion, divided by the concentration of my reactant, which in this case was acetic acid. So my acetic acid is turning into acetate. All right, so A says, at the half equivalence point, the acetate ion equals the acetic acid concentration. So the log term is equal to 0. Why is that? Because 1 over 1, or if they're the same number, divided by itself is equal to 1. The log of 1 is 0. So we can kind of cross that whole part out of the equation. Your pH is equal to your pKa at the half equivalence point. All right, so mathematically this isn't too bad, right? All we have to do is figure out the pH at the half equivalence point. Okay, and I'm just going to make this up. I'm just saying it's 3.4. Again, this is not correct. All that you have to do is rearrange this equation. Your Ka is equal to 10 to the negative 3.14. And again, not the actual value. Okay, moving on to question 4. We're going to skip step A. It's just information, so we're going to move on to step B. But it's kind of important to remember the reaction that took place, right? We had acetic acid, and this is just a net reaction. Formed hydronium ion H3O plus acetate ion CH3CO2 minus. Okay, so moving on to step B. At the equivalence, the pH is above 7 because the hydrolysis of acetate ion occurs. Focus on the hydrolysis part. That's what really matters. So we're going to write out that hydrolysis reaction. That's our Kb reaction. So we have our acetate ion reacting with water, hydrolysis, breaking down of water, and it's going to reform acetic acid and hydroxide, OH minus. All right, so that's our reaction. We'll come back to that in a bit with an ice table, but for right now, let's just move on to part C. So part C, the pH at the equivalence point can be used to calculate the OH minus, or the hydroxide, concentration at equilibrium. All right, so I'm just making this up, and I'm just pretending that the pH was 7.8. Again, this is not the correct value. Make sure you get the right one from the lab. But you can plug this into Kw, or the equilibrium constant of water, and just remember that is equal to the concentration of H3O plus, or hydronium concentration, times your hydroxide, which is your OH minus concentration. All right, remember we talked about this before. pH is the concentration. It's just a way of expressing the concentration of hydrogen in solution, which is the same as the hydronium. So rearranging our log, we get 10 to the negative 7.8, which is equal to our H3O plus concentration. We know that the Kw, or the dissociation constant of water, is 10 to the negative 14th. So rearrange that equation, and you get your concentration of OH minus, or your hydroxide concentration, at equilibrium. Now I'm lazy, I don't want to put this into my calculator, so I'm just going to keep this as 10 to the negative 14th divided by 10 to the negative 7.8. Now I'm just going to take that and plug that in as my equilibrium concentration of hydroxide. All right, let's fill in what we can, right? So there's my equilibrium concentration of hydroxide. Again, I should have no products initially, and I should be going from 0 to some value. It's all 1 to 1. And then our initial concentration of acetate is just going to be our total moles of acetic acid from the beginning divided by our total volume, which is our titrant plus our initial volume.